So, hello everyone again. This is lecture 6 part 3 of semiconductor electronics, materials, devices and simple circuits. So, in this we will be starting with the new discussion, that is regarding your photodiodes. Okay. So, let us begin the discussion directly. In the previous chapter, previous discussion, we have understood about the xenodiodes, the working of xenodiodes, how can xenodiodes be used as a voltage regulator, one of the examples related to it. Let us now begin optoelectronic devices. The first type of optoelectronic devices, which was the example given in the previous discussion, which was based which is called as your photodiodes. Okay. So, let us start the discussion here. So, I am Sameer Lavankar. Let us begin our discussion. So, currently we are on the 8th topic here, that is your special purposes PN junction diodes. Okay. So, here the first thing which we understood was about xenodiodes, and the second thing which we are understanding here is based upon optoelectronic devices. Fine. So, let us start the discussion directly. So, optoelectronic devices, so this was basically explained to you in the previous discussion also, as in the previous everything which you have understood about semiconductor diodes previously was applied was done under applied electrical inputs, correct. Now, we are trying to use some another ways in which photons are being applied for the in this semiconductor diodes. Okay. So, let us understand this concept here about photodiodes and then we can move forward. Okay. So, let us understand this concept. So, a photodiode is again a special purpose PN junction diode. So, everything we are talking about is PN junction diode only. Okay. So, a photodiode is again a special purpose PN junction diode fabricated with a transparent window. Fabricated, so a transparent window is being actually on this PN junction diode here. Okay. So, a photodiode is again a special purpose PN junction diode fabricated with a transparent window to allow light to fall on the diode. So, basically allow the light to fall on this diode. Okay. It is operated under reverse bias. Again please remember, please keep on remembering this. Okay. This is very important, that which of these diodes work in forward bias and this which diodes work in reverse bias. Okay. Fine. So, it is operated under reverse bias when the photodiode is illuminated with light. So, when this photodiode is illuminated with light or photons with energy h nu greater than the energy gap E g of the semiconductor, then electron hole pairs are generated due to the absorption of photons. So, if you have understood the concept of dual nature of radiation and matter, which was one of the chapter in physics, you know clearly that when amount of energy which is h nu of the photons is being injected upon the electrons get ejected about. Okay. So, that concept is only being applied here. So, when the photodiode is illuminated with light, okay. So, when the photodiode, so this is the basic, this is the photodiode, and when it is illuminated by light, what happens is with light with energy h nu which is greater than the energy gap E g of the semiconductor, then electron hole pairs are generated. So, we get an electron also, and because the electrons are being ejected, so therefore, we get an electron also, and because it is ejected from a location, therefore, we get a hole also. So, electron hole pair is being generated due to the absorption of photons, fine. Next, the diode is fabricated such that the generation of EH pairs, that is electron hole pair, takes place in or near the depletion region of the diode. So, majority of the work is being done near the depletion region, which is this. Okay. So, the diode is fabricated such that the generation of EH pairs takes place in or near the depletion region of the diode. Okay. Fine. Next thing is, due to the electric field of the junction, electrons and the holes are separated before they recombine. Okay. So, that is one of the property, it is quite evident. So, first of all we should know that what is happening. So, this is your depletion region. In the depletion region there is an electric field happening, and because of this electric field and because of the repulsion of the electron and the holes, those are being separated apart from each other. Okay. So, due to the electric field of the junction, the electrons and the holes are separated from before they recombine. So, they would try to recombine. It is quite evident that if there is a positive charge, there is a negative charge, they will try to recombine, but because of the electric field existing near the depletion region, it is very difficult for them to recombine. Okay. So, basically they do not recombine. So, due to the electric field of the junction, electrons and holes are separated before they recombine. The direction of the electric field is such that the electrons reach n side, the electrons reach N side. So, this is how, this is where the electrons reach, okay, and similarly the holes reach P side. Okay. Next, electrons are collected on N side, quite evident. So, as you can see, electrons are collected on N side and holes are collected on P side, giving rise to an EMF. So, quite evident, if there is some amount of charges being present here and some another amount of charges are present here, which are not able to release or which are not able to get recombine with each other. So, because of this, a concentration would be happening and this concentration difference would lead to an EMF being produced. Okay. So, this EMF is nothing but an electromotive force, which I think you may have studied in the chapter of electromagnetic induction. Okay. Fine. So, so this can be understood as EMF can be understood as nothing but a voltage only. Okay. So, electrons are collected on N side and the holes are connected on P side, giving rise to an EMF. When an external load is collected, when an external load is connected, then the current flows. So, when you try to connect this external load, then the current flows. How can we see that the current is flowing? You can use a galvanometer for this. So, you know that galvanometer will deflect when the current is being passed through it. Okay. Fine. Next thing is the magnitude of the photocurrent depends on the intensity of the incident light, that is photocurrent is proportional to the incident light intensity. So, this is again a topic which was being cleared in very detail when we were understanding the concept regarding your dual nature of radiation and matter, in which we understood that what happens, what is the effect of this intensity phenomena, then frequency, then wavelength, etc., on the light or on the electrons. Okay. So, that thing is only been explained again here. So, the magnitude of the photocurrent depends on what? It depends on the intensity of the incident light, that is photocurrent I is proportional to the intensity of the incident light. Okay. So, as you can see that the value of the voltage is, so this is the current, as you can see that this is keep on increasing. Okay. So, as the intensity is increasing, you can see that the amount of current is also increasing. Okay. So, that we can we can say that this current is directly proportional to your what we can say, intensity. So, as you can see, the intensity is keep on increasing. Fine. So, let us move forward. So, now it is easier to observe the change in the current with the change in the light intensity if a reverse bias is applied. Okay. So, it is how it is easier. So they are just trying to explain this phenomena here. Okay. So, they are just saying that it is easier to observe the change in the current with the change in the light intensity, change in the current. So, change in the current with the change in the light intensity, if the reverse bias is applied. So, this can be observed clearly in the reverse bias. Okay. Thus photodiodes can be used as a photodetector to detect the optical signals. Okay. So, how it can be used? So, for that, if something H nu is being acted upon it, so basically we can detect that if the galvanometer is showing some sign, then it is quite evident that there was some photoelectric or what we can say, photons are being detected. Okay. So, some photons are being acted upon it. So, thus photodiode can be used as a photodetector. So, what does photodetector mean? So, detecting the photons is basically photodetector to detect the optical signals. So, optical signals can be detected. How it can be detected? There will be a series circuit being present there, and if there is a deflection in the galvanometer being observed, then we can say that yes, the optical signals are present there. Okay. Next thing is the circuit diagram used for the measurement of IV characteristics of a photodiode is shown in the figure A. Okay, so this is the circuit diagram used for the measurement of IV characteristics of photodiode, and typical IV characteristics in figure B is shown here. Okay, so that is the explanation being done. So we have understood till now two different diodes. One was your Zener diode, the second was your photodiodes. Till now both of them were in reverse biasing only. Fine. So, now let us understand one of the examples related to these topics. Okay. So, the example says that the current in the forward bias is known to be more than the current in the reverse bias. So, this is a concept which we know quite efficiently, correct. So, in forward bias the current is due to your diffusion, and in reverse bias it was basically due to the drift. Okay. So, therefore, diffusion is in milliamperes and drift basically was due to your the current in the reverse bias is due to drift current. Okay. So, what is the reason then to operate the photodiodes in reverse bias? Okay, so, why we are trying to operate in reverse bias, why we are not operating in the forward bias? Okay. So, let us understand this solution. So, this is just the extension of the previous part only, so that we can understand why we are working in reverse bias and not in the forward bias. Okay. So, let us first of all take the consideration of a n type semiconductor. Okay. So, just to make you revise, what is n type semiconductor? So, in an n type semiconductor, what is the majority charge carrier? So, majority charge carriers are electrons only. What is a minority charge carrier? These are holes. Okay, fine. So, now let us understand. So, consider the case of an n type semiconductor. Obviously, the majority carrier density n is considerably larger than the minority hole density p, quite evident. The density of the electrons will be greater than the density of the holes, clearly, as you can see above also, that is n is greater than p, clear. On illumination, so on illumination as in when the optical signals are being detected, when we are trying to detect optical signals, let the excess electrons and holes generated be delta n and delta p. Okay. So, we know from the previous discussion that when the optical signals are being generated, then an electron hole pair is generated. This electron hole pair is being separated apart, they cannot be recombined. Why? Because of the electric field existing in the depletion region, and because of this separation there is a concentration gradient happening, and that is what leads to your EMF, correct. So, the basic crux is that if there is a optical signal being interacted upon, then there is an electron hole pair being generated. That means, there will be an increase in the delta n value also, there will be an increase in the delta p value also. Okay. So, on illumination, let the excess electrons and the holes generated be delta n and delta p respectively. Therefore, what we can say that the new density would become n is delta n dash is equal to n dash n dash is equal to n plus delta n, and similarly p dash is equal to p plus delta p. Here n dash and p dash are the electron and the hole concentrations at any particular illumination, and n and p are the carrier concentration when there is no illumination. So, you can understand this quite clearly that when there is an illumination being added upon, then an electron hole pair is generated. Because there is an electron hole pair generated, there is an increase in the density of majority carrier also, and there is an increase in density of the minority carrier also. Therefore, the new density n dash is equal to n plus delta n, and similarly the new density p dash is equal to p plus delta p. Fine. Now, remember delta n is equal to delta p. Okay. So, we as I was saying also that whenever a optical signal is being added upon, we knew that an electron hole pair is being generated. So, if a pair is being generated, it is quite evident that for each and every electron being generated, there is a hole being generated. So, if there are 5 electrons being generated, then it is very efficiently can be said that there are 5 holes being generated. Okay. So, thus delta n is equal to delta p, but we know that n is very greater than p. Okay. Hence, the fractional change in the majority carriers, that is delta n by n, would be very less than the minority carrier, that is delta p by p. Okay. So, I think this can be understood from the diagram only, from the mathematical expression which is written here only, or else I can explain you using this also. Let us say, take an example, let us say n is 1000, let us say p is 10. Okay. Let us say delta n, which is equal to delta p, is equal to let us say 2, fine. So, please explain me. So, it is quite evident. So, it is quite evident that n is greater than p, correct. So, now if we calculate the value of delta n by n, what will be this value? This value will be nothing but 2 by 1000. If I calculate this in percentage, then this will be equal to 0.2%, correct. Similarly, if I calculate delta p by p, what will be delta p by p? Delta p by p would be equal to 2 by 10 into 100, which will be equal to 20%, right. So, you can see clearly that the fractional change in the majority carrier, that is delta n by n, would be very much less. It is just 0.2% and it is 20%. So, you can see the amount of difference in the majority carrier concentration and the minority carrier concentration, fractional change basically. And this is just a case which I took as 10,010. The original quantity is something which we have made as an example also. We in the discussion when we are talking about just after extrinsic semiconductor, when we did a formula based question about Ne into Nh is equal to Ni square, we understood that there the amount of Ne was approximately 10 to the power 3 times higher than the value of Nh. Okay. So, from there also we can understand that if only for the order of 2 this is the case, then what will be in the order of 3, 4 etc. Okay. So, hence the fractional change in the majority carriers would be very much less than that in the minority carrier, that is delta p by p. So, I explained you this line using the example also. So, in general we can state that the fractional change due to the photo effects, on the minority carriers dominated the reverse bias current is more easily measurable than the fractional change in the forward bias current. So, they are just trying to say that because this delta n by n cannot be calculated very much easily as compared to this delta p by p, the fractional change can be observed here much more clearly, and that is why we do the complete concept in your reverse bias. Okay. So, let me read the last line again. So, the last line simply states that in general we can state that the fractional change due to the photo effects on the minority carrier dominated reverse bias current is more easily measured than the fractional change in the forward bias current. Hence, photodiodes are preferably used in the reverse bias condition for measuring the light intensity. So, just because the fractional change in majority carrier is very less, therefore, it is much easier, or we can say that the minority carrier dominated reverse bias current is more easily measurable. So, thing which is more easily measurable would be used at a very more efficient state, and that is why we use it. Okay. So, in general we can state that the fractional change due to the photo effect on the minority carrier dominated reverse bias current is more easily measurable than the fractional change in the forward bias current, fine. So, that being said, photodiodes are preferably used in the reverse bias condition for measuring light intensity. Okay. Okay, so that is the completion of your Zener based example and your photodiodes. Now, I will start this new thing which is light emitting diode in the next discussion only. So, let me stop it here only. We will just revise 2-3 conditions. So, first of all, the things which you should remember for your exams. So, first thing is every time please remember the VI characteristic. These VI characteristics are very important for the exams. So, till now we have understood the VI characteristic of 3 different concepts, correct. So, we have understood this for simple forward and reverse bias concept in the semiconductor devices. Then in the second thing which we understood, this was based upon your Zener diode, and the third time which we understood this was based upon your photodiode. Okay. I think many more VI characteristics would come into picture. So, I would say suggest you to just keep on practicing these all concepts so that it will be clear when the exam appears. Okay. Okay, one more thing here. So, this concept which was involved here was based upon the understanding of your dual nature of radiation and matter. So, you can just refer to those lectures and understand these concepts there also. Okay. Then also please remember for each of these concepts whenever the operation is being done in forward bias and when it is done in reverse bias. Okay. So, till now the 2 diodes which we understood, first was your Zener diode and second was your photodiodes, both were operating in the reverse bias condition only. Okay, fine. So, that thing being said, So, the course progress till now. So, we started with the introduction part, then the classification of metals, conductors and semiconductors, then the intrinsic semiconductors, then the extrinsic semiconductors, in which we understood p type and n type semiconductor, that is n is having a pentavalent impurity, p is having a trivalent impurity. Then a p-n junction diode, in which we understood the complete concept of depletion region. Then the semiconductor diode, that is basically a p-n junction with a metallic contacts. In this we understood the concept of forward biasing and reverse biasing. Then the application of junction diode as a rectifier, in which we understood the half wave rectifier, then a full wave rectifier, and then using a filter. Okay. And then finally, we are on the 8th topic, that is special purpose p-n junction diodes, in which we are understanding right now about photodiode, which was completed. Then we will start in the next lecture regarding light emitting diode, and xenodiode is completed. Okay. So, xenodiode is being done. Then photodiode is also done, and next thing which we need to start is basically light emitting diodes. Okay. Then after this, I think we will move on to solar cell and then move forward. Okay. Finally, after this 3 things are remaining. One thing is junction transistor, next thing is your digital electronics and logic gates, and finally the integrated circuits. Okay. So, let me stop the discussion here only. So, we will meet in the next lecture. Till then, thank you.